Hello, all. I'm Professor Archana Buruswari, working in the Computer Engineering Department. In this video, we are going to discuss the deadlock detection algorithm in operating system. As we know that to handle the deadlock, there are the four ways. That is, the first one is deadlock prevention, then deadlock avoidance, then deadlock detection, and deadlock recovery. Okay, so the first two ways, that is the prevention and avoidance, try to prevent. First way is to prevent a deadlock by preventing one of the four necessary conditions. The second way is avoidance, deadlock avoidance algorithm. It is used to avoid the algorithm. And this is the algorithm which we are going to discuss in this today's video. That is the deadlock detection. It allows the system to enter into the deadlock, and then detection algorithm checks whether the deadlock has occurred in the system or not. So that is the deadlock detection algorithm. And if the deadlock detection algorithm detects that there is a deadlock has occurred, then there is a fourth way, that is the deadlock recovery. So using recovery scheme, we can recover the system from the deadlock. Okay. So we'll continue with this deadlock detection algorithm. So deadlock detection, what it does basically, it allows the system to enter into the deadlock state. So detection algorithm basically is a technique used by an operating system to identify deadlocks in the system. This algorithm checks the status of the processes and resources to determine whether any deadlock has occurred and takes the appropriate action to recover from that deadlock. So that appropriate action to recover from the deadlock has to be taken care by the recovery scheme. So, as we are looking here into the deadlock detection algorithm, so in deadlock detection, again, there are two parts we can say that. So, what are that? So, first one is the algorithm is for finding whether the deadlock has occurred using a single instance of each resource type. Now, what is a single instance of each resource type? As we know that there are the multiple resources available in the system, right? Like memory cycles, CPU, disk, IO cycles, different IO devices, and many more resources are there available in the computer systems. So these resources can be a single, it can be, there can be only a single instance of each resource type. For example, CPU. If the CPU only one CPU chip on your in your system, then a CPU resource is having only one instance. If your system is a quad core, then CPU resource having the four instances, right? So if we suppose assume that there are only a single instance of each resource type in the system, then we'll follow this algorithm. If there are the multiple instances of each resource type, then the different algorithm to find the data. So there are two variations are there. Okay, one is true when there is a single instance of each resource type, and the other variation when there are the multiple instances of each resource type. Okay, we'll continue with the slide, that is single instance of each resource type. So in this, there is only one instance of each resource type is available in the system. So what it does here, it maintains the wait for graph. Now what is the wait for graph? Wait for graph is same as a resource allocation graph, or it can be built from the resource allocation graph. We already know the resource allocation graph, which is used in the deadlock. Okay, so here in the mid in so here in this algorithm, we'll maintain the wait for graph, which we need to construct from the resource allocation graph. So what are the contents of this particular wait for graph? The wait for graph contains only the nodes. The nodes can be the threads or the processes. The nodes can be the threads or the processes. And if there is a edge going from one thread to another thread or one process to another process, for example, here the uh, direct edge is going from TI to TJ. It means what? The TI is waiting for TJ. So TI is waiting for TJ means what? TI is waiting for the resource which is held by TJ. TI is waiting for resource which is held by TJ. So that means the TI is waiting for TJ. So periodically it invokes an algorithm that searches for a cycle in this graph. If there is a cycle in the wait for graph, then there exists a deadlock. So an algorithm to detect a cycle in a graph requires an order of n square operations where n is the number of vertices in the graph. So what are the vertices here? Vertices is the number of processes or number of threads. We'll see one example, so we'll get it You will understand it more better way. Suppose this is a resource allocation graph. Okay, resource allocation graph consists of the vertices and the edges, right? So, but in resource allocation graph, the vertices can be of two types. Vertices can be of two types. You can see here, there are two types of vertices. One is resource and another one is a processes or threads. So, circular one is for the processes or threads, and the rectangular thread vertices are for the resources. Okay, and there can be the different kinds of edges in the resource allocation graph. If the edge is going from the process to resource, it means what? The process is requesting that particular resource, that is called as a request edge. If a edge going from resource to a process, if a edge going from resource to a process means what? This particular resource has been allocated to that particular process, so that is called as a allocation edge. So two types of edges are there, request edge and allocation edge or assignment edge. This particular resource has been assigned. Okay, so this is a request edge and this is assignment edge. So this is the resource allocation graph that we already know that. Now from this graph, we have to construct the weight for graph. From this graph, we have to construct the weight for graph. So what is the formula? It is very easy. If there is a any edge, weighting edge from one thread or one process to another process. For example, you can see that here T1 is waiting for the resource R1 and T2 is holding the resource R1, right? So in wait for graph, we don't have the resources here. We have only the threads or processes, and we can add the waiting edge over here. Okay, as T1 is waiting for R1 and R1 is held by T2. So directly we are giving here edge T1 to T2. So T1 is waiting for T2. Then T2 is requesting for R4 and R4 is held by T3. So we can have the edge from T2 to T3. Then for T3 again we can see here T3 is requesting for R5 and R5 is held by T4. So we can have the edge from T3 to T4. Then from T4 to T4 to T1 also you can see that T4 is waiting for the resource R2 and R2 is being held by the T1. So we can directly add the edge going from T4 to T1. And finally you can see that here the T5, T2 to T5 edge is also there. T2 is waiting for the R3 and R3 is held by T5. So that directly we are adding the edge from T2 to T5. So this is the corresponding weight for graph for this particular resource allocation graph. So now when there is a single instance of each resource type, we are going to construct the weight for graph from the given resource allocation graph. And in this graph, we need to check whether their cycle exists in the graph. If the cycle exists in this graph, then there is a deadlock. If the cycle doesn't exist, then there is no deadlock. Okay, so that is a single instance of each resource type. When there is a single instance of each resource type, we have to use this particular method. Now we'll see the second method. When there are several instances of resource type, so this algorithm employs several time varying data structure. When there are the several instances of each resource type. Okay, so which data structure it employs or it uses? So it uses the available. So available is one of the vector of length m, indicates the number of available resources of each type. Indicates number of available resources of each type. Then allocation. The allocation is basically the matrix. It is n by m matrix where n is the number of processes, m is the number of resources. Okay, so it is n by m matrix defines the number of resources of each type being currently allocated to each thread or process. The next one is the request. So request is again the matrix, again n by m matrix, that is the process and resource ka matrix. It indicates the current request of each thread. It indicates the current request of each thread. If request of ij is equals to k, means what? Thread I ti or process ti is requesting k more instances of resource type j. K more instances of resource type G. So this is the time varying data structure we need to have, we need to implement over here. So in detection algorithm, so this detection algorithm, we can also call it as a safety algorithm. Because in Banker's algorithm, there are two sub algorithms under the Banker's algorithm, that is a safety algorithm and resource request algorithm. So this detection algorithm is some same as a safety algorithm only, but we have to use some different terminologies in this algorithm that we'll see how we are going. So let here work and finish be the vectors of length m and n. Let work and finish be the vectors of length m and n. So these two terminologies basically we are going to use here in the detection algorithm. So respectively initialize work is equals to available. Available means the number of resources which are currently available. So we are initializing it to the work now. And for I is equals to 1 to n means for all the processes. For I is equals to 1 to n or 0 to n minus 1. Okay, what we are doing means for all the processes, if allocation is not equals to 0, then finish of I is equals to false, because till now none of the process has finished it. All the processes are in the queue for getting executed. Okay, so what we are making, we are initializing one of the flag, finish flag for each process as a false initially, because none of the process gets executed. Otherwise, if the process is gets executed, whenever the process gets executed, that time we need to make that finish flag of that process as a true. Okay. So here, second step will this is the algorithm second step. So here, find an index I such that both finish of I is equals to false. So obviously we start from the first process itself here. So finish of I is equals to false. Yes, initially the first process finish status is false. Then we'll check if this particular status is false, then we'll check the request of that particular process. The request of resources for that particular process is less than equals to work. Request of that particular process, that is ith process, is less than equals to work. If it is less than equals to work, work means what? Available, right? We are already initialized into the step 1. So if it is less than equals to work, means yes, we can allocate those many resources. We have those resources in the system. Okay, if both of the conditions are true, then we can allocate the resources and we can execute this particular process. But if no such I exists, if both the conditions are false, if no such I exists, we'll go to step 4. So what is the step 4 here? Step 4 is equals to E. Here you can see that if finish of I is equals to false for sum of the I from 1 to n, then the system is in the deadlock state. Or moreover, if finish of I is equals to false, then that particular thread or process, I thread or I process is dead. Okay, so this happens when there is no such I exist in the step. But if there such I exists in the step 2, it will not go to the step 4, it will go to the step 3. So what is the step 3? Step 3 is equals to what we are saying. If in step 2 we have checked that key finish of I is equals to false and work of that the request of that particular process is less than equals to work. So basically we can allocate resource. So means what? We are pretending to execute that process. We are pretending here that we are executing that process. So after execution, what is the thing? The process has to release the resources. So here we are releasing the resources. How we are releasing? By using the step 3, work is equals to work plus allocation of ith process. ith process जो अभी अभी execute हुआ है, whatever the allocation of that we are going to add to the work. So work will get increased. Work means available here. So work is equals to work plus allocation of I. So the process is releasing all the resources and we are adding those resources to the work, and we are making the finished status of that particular ith process as true, of that particular ith process as true. So once this particular step is done, we'll again go to the step 2 for second next I, because it will be in the for loop, right? First process is done. Now we need to do this all the steps again for the second process, third process, fourth process, and so on, unless and until all the processes are finished. Okay, so this is the simple deadlock detection algorithm. When we have to implement this algorithm, when there are multiple instances of each resource type. Okay, so this algorithm requires an order of O of m into n square operations to detect whether the system is in deadlock state or not. Okay, We'll see one example for this, so you will understand it in more better way. So suppose this is the example given. The system is given 5 processes are here: P0, P1, P2, P3, and P4. Here it is the allocation matrix, request matrix, and available vector. Okay. So initially, what we need to do in this, work is equals to available. Work is equals to available means this one. So work is equals to 0, 0, 0 because our available is equals to 0, 0, 0. Right? Now after that, finish is equals to false for all the processes. जो finish flag होगा, finish flag for all the processes we need to make it as a false because none of the process gets executed till now. Now we'll start with the first process. So I is equals to 0 is selected, right? As both finish of 0 is equals to, so for this I is equals to 0, we need to check finish of 0 is equals to false. Yes, it is false. And work or request of this P0, this is the request of P0, is less than equals to work. Yes, it is less than, it is equals to work here. So we can execute that particular process. So here we are pretending that the I0, the process I is getting executed. Process I means here P0 process. Okay, so what we need to do, work is equals to work plus allocation. Work is equals to this 0, 0, 0 is work and allocation of this particular process, that is 0, 1, 0. So we are adding it up together. So now our work is increased. So now it becomes 0, 1, 0. And after this, we need to make that particular process finish flag as a true because it is executed. Finish flag as a true because it's executed. Now we need to make this I is equals to 1. So for I is equals to 1, it will check finish of I is equals to false. Yes, finish of I is equals to false for I is equals to 1 value. And request of this one, P1, 202. 202 is less than equal to 010. No, it is not less than equal to 010. So we need to stop here and we need to go for the next process. So I is equals to 2 is selected here. That's why. As both finish of 2 is equals to false here and its request is 01000, which is less than equals to 010. So the condition is true. So what we need to do, we are pretending here again the P2 process is getting executed. So work is equals to work plus allocation. So जो भी allocation है उसका, that is a 303, that we are adding it over here. And now our work is updated to the 313 here. And make the finish of that particular process as true. So that is P2 is true now. Now we'll go to the next process. So again, we'll go to the I is equals to 1, check whether the finish of I is equals to false. Yes, one finish of 1 is equals to false. And request of P1 is less than equals to work. Yes, it is less than equals to work now because our work is updated. So here the P1 gets executed. Again, after executed, here release the resources by the P1. So that is work is equals to work plus allocation. Update the work here and make the finish of that particular process as true. Then I is equals to 3 is selected. Check both the condition here. Okay. If it is false and the request is less than equals to work, then again execute the process, pretend to execute the process, update the work by releasing the allocated resources and make its flag as a true. And then the final process I is equals to 4 is selected as here. Both finish of 4 is equals to false. And again check the request of process 4 is less than equals to work. Yes, it is less than equals to work here. So update the work. Work is equals to work plus allocation. Now my work is updated to 726 and then make the finish of last process P4, that is true. So at the end you can see that the finish is a vector of all true. Finish is a vector of all true. Means all the processes are executed. It means that there is no deadlock in this example. It means that there is no deadlock in this example. So we have seen the deadlock detection algorithm, one example to check whether the deadlock is there in the system or not. So in this example, there is no deadlock. So now we'll do some changes in the same example to see that whether the deadlock is there or not. Okay. So the same example, and this is the sequence for that. That is the step sequence. That is the last example which we have seen. So P0, P2, P3, P1, P4 will result in finish of I is equal to true for all I. So the system is not in the deadlock state. Now we'll make one small change in this example. What we do? The request of process P2 is what? 000. So if I increase it to 001, if I increase it to the 001, right? If I increase it to 001, so in that case, here, see, process P0 will get executed initially because request is less than equals to word. Then P2, P2 will get executed. It will try for P2, but P2's request is now instead of 00, it is 001. So we'll go and check. 001 uh, can we satisfy the request? No, because after executing the P0, our work is updated to 010 and our request is 001. So 010 is less than equals to 001? No, in that case. So it will not be able to execute. So can we reclaim the resources held by the thread or process P0, but insufficient resources to fulfill the other processes request. So what it happens here, we cannot execute the T2 or P2 here. And so if we cannot execute the particular next thread or process, so T1, T3 and T4 also will not get executed. So basically the deadlock exists here, and which is consisting of the processes T1, T2, T3 and T4. Only first process gets executed, and after that all the processes are in the waiting state because they are waiting for the one of the other processes to release the resources, and no one is able to release the resource because all are in the deadlock state. So this is the deadlock state. So we have seen the deadlock detection algorithm with example when there is no deadlock, and the another example when there is a deadlock. So thank you for this particular video, patient listening. Let's see you all in the next video.